circles that are externally tangent at a point T. Let me draw that like this. So I'll call this T. And this I'll call it O1. And this I'll call it O2. All right. And then we have a quadrilateral. So I'll draw like this. So it's tangent. Sorry, this is covering it up a little bit. But basically, we have like a point E and a point F. And if we draw the tangents at E and F, it cuts this other circle at A, B, C, and D. So draw that tangent and this tangent. Let's make sure that they intersect the circle. Kind of like that. So DA is tangent. So it's kind of like this. Actually, let me see, because I wanted to bisect AB. Let me do it like this. So this should be A. I think that looks better. So DA is tangent at E, and CB is tangent at F. BN bisects angle ABF. So if I draw the angle bisector of ABF, that almost looks parallel, but I don't want it to look parallel. So is it parallel? Yeah, no, it's not. Okay. So the angle bisector of ABF meets EF at N. So this right here is point N. And FT meets arc AT at a point M. So I'm going to clean this up later, make it look nicer. But this would be point M. And we want to show that M is the circumcenter of BCN. So let me, maybe that looks a little better. Okay. So let me hide a couple things. All right. And is it CT and N? Oh no, it's so BN is the angle bisector. Okay. So I'll have to remember that. It almost looks like ABF is a, well, that doesn't look that much like a right angle. So yeah, this is the figure. And we want to show that M is the circumcenter of BCN. So is it obvious first that MB is equal to MC? I think that's probably just an angle chase if I had to guess. We want to show that MB is equal to MC. Because angle MBC, it's arc MT, half of arc MT plus CT. And angle MCB, it's CMF, which is arc CT plus this angle, which is the same as this angle. So yeah, it might help to draw the, you know what, I'm going to draw this. It just might help with the angle chase later. So we want MB squared is equal to MT times MF. And I extend TB and TC to meet the other circle. Yeah. JI is parallel to BC. Oh yeah, that's by homothety, that has to be true, right? So not only that, I mean, anything that we can get from the homothety, like MC is parallel to JF, MB is parallel to FI. Yeah, anything we can say using the homothety is true. MJ is parallel to CF, or no, not really. Yeah, I think MC and JF are parallel, right? Yeah, there's a lot of stuff that's true by homothety. So let me check something here. I wonder. So I'm getting that. Is it true that this angle TFC is equal to MBT? Is that obvious? Because that. Oh yeah, because BM is because that's equal to that, and by homothety those are parallel. So yeah. So yeah, I could show MBC as isosceles. The hard part is showing M and B is that N also lies on that circle. Oh, so when is the class? So it's over at 1 p.m. So in about an hour and a half. But if you want to leave early, you can. So yeah, usually I do it for 3 hours. But yeah, I know in other countries it's often late at night or at a difficult time. So yeah, if you have to leave early, don't worry about it. A, M, and N. Let's see if they're collinear. They do look collinear, at least. But let's see if I move. Ah, looks like they are collinear. Okay. So yeah, let's see if we can show that. So yeah, we have to use the angle bisector thing somehow. Yeah, how do we use that angle bisector condition? I'm not even sure where to start with that. So what if I drew that circle? Maybe it might help to see something. So yeah, what would be the case if A, M, and N were collinear? So we haven't proven it yet, but I wonder if that would help us solve it somehow. I wonder. So what if we draw this point? Because since BN is an angle bisector, if we draw this point, that would mean arc KN and NC are equal, right? So maybe that might help. BN, can I label BN intersect? Yes, so we'll draw that. There. I wonder if L is the midpoint of arc M. No, it's almost true, but it looks similar to Sawayama. It does a little bit. Maybe. Okay, let's see. So K. Let's see. This is a hard one. Let me see if there's anything special about this point K. Or K, I think, oh no, K, L, and T, I don't think are linear. Yeah, I don't see anything special about point K. Maybe, I don't think those are concurrent, but let me check. Yeah. Yeah, I was hoping. Yeah, I don't see anything special about this point K. Maybe I should delete it. But yeah, and then I don't know how to use this angle bisector thing. That's hard. Well, I guess AL is equal to LC. That's kind of why you wanted me to draw this point, right? Is LA equal to LN? Good question. Yes. So I think that is probably a key fact in solving the problem. So L looks like the circumcenter of A and C. So we know LA is equal to LC. So N would be the excenter. Wait, why would that be true? Oh, because this is the midpoint of arc. Yeah, so N is the excenter of triangle ABC. Yeah, interesting. N is the excenter of ABC. So we want to show that if we take the excenter and we connect it to A and let it be M. So yeah, we can erase like the whole picture then. If that's but first we have to prove that. So that's weird. So if you take the excenter of ABC and you connect it to A and it intersects the circumcircle at a point, then that's the circumcenter of BCM. Is true by an angle chase. So we know MB is equal to MC. So we can compute ALB and show it as twice LAM. Yeah. Because this is like, So basically, AN is the bisector. Wait, if M, wait. So N is the excenter. So yeah, so this has to be an angle bisector. AN bisects. Yeah, I think we could probably do an angle chase to show that if we can show that. So how is M defined? M line FT. If we can show that AM is the angle bisector of KAC, oh, but we'd also have to show AM and N are collinear. Yeah, we don't know that yet. Do you mean A, N, and M, or when you say E, N, and M are collinear? E, N, and F. Yeah, I think that's by definition, right? Because N is defined to be the intersection of this angle bisector with EF. Let's see, maybe. No, MA isn't necessarily equal to MT. It just looks like it in that figure. The excenter passes through EF. Oh, Sawayama's theorem. How does Sawayama's theorem tell us that the excenter passes through EF? So with Sawayama's theorem, you have like curvilinear in circles, right? Yeah, explain how Sawayama's theorem proves that. Oh, okay. So yeah, what if we let N be the excenter and then we show that E, N, and F are collinear? That might be, so we could start by letting N be the excenter. Then it might not be that hard to show that A, M, and N are collinear. And then we could try to show N lies on EF.
Could you prove that AMN is collinear?
Yeah, I can't prove the way that N is defined in the problem. I don't know. I can't prove that yet. So really, yeah, really, I'm not sure why that's true, or I don't know the proof of it.
Yeah, we were gonna prove that because if we have A and M is collinear, so the problem has been solved.
Oh, you think you could solve the problem once you show that those three are collinear?
Yes.
All right. And so once you know those are collinear, how does that solve?
Yeah. Yes, I can prove that MB is equal to MC.
Mm-hmm. So yeah, so MB equals MC. I think I could prove that using an angle chase. And then how do you show that's what's the rest of the proof to show it's equal to MN?
Okay. So hold up. Just let me some.
It's all right. Yeah, maybe there's a way to show like angle BNC is twice angle BMC or something like that, or half of it. I mean. Yeah, actually, I think it would just be an easy angle chase then. Like once we know that AM and N are collinear, then that would mean that N is the excenter, and then I think that would solve the problem, because then we want to show M is the circumcenter of BCN, but so that's kind of the same as showing angle BNC is half of angle BMC, and I think that's just an angle chase. So yeah, I think yeah, once we show that AM and N are collinear, yeah, I agree, it's an easy problem. All right, so yeah, that's the key. How do we show AM and N are collinear? Or what we could do is we could let N be, we could define N prime to be the excenter. And then we want to show N prime lies on EF. Either way would solve the problem. So yeah. Let's see. All right. Can I draw 0102? Yes. So I have one idea. So basically, we want to show that the excenter of ABC lies on EF, right? So what if I extend AB to meet EF at a point? Then by the angle bisector theorem, if we drew the angle, I'm just thinking about this. Yeah, what's the best way to show that the excenter of ABC lies on EF? I mean, that's basically all we want to do, right? If we can show that, we solve the problem. I think that's like a nicer way of phrasing it. So I guess if we could show the distance. I'm thinking maybe we can use the in-center, x-center lemma somehow. Can we somehow compute angle NMF or angle NMC? Not sure. Let me try. Maybe there's like a cyclic quadrilateral that we're missing. No. But yeah, the way I'm thinking about the problem is like if we could basically erase almost everything. We just want to show that the x-center of ABC lies on EF. So that's one way to think about it. It seems like it would be it seems like it should be a simple problem, but maybe it's not as simple as it looks. So basically, you know what that means? If we move O2 around, N should stay exactly the same. That doesn't look true. Oh no, because it's changing triangle ABC also. So that's why N doesn't stay the exact same point. But yeah, basically it's saying if we could move just O2, but this circle would stay the same, then it says N would stay the same basically. So it says as we move O2 left and right, EF would always pass through this point. It's kind of interesting. Yeah, so I'm kind of curious. So I'm thinking about like drawing a different picture. I'm going to try something. Sorry, guys, but I'm just going to try something just for fun here. So it's like saying, let's say we have this. And oops. So basically, if I draw the tangents, where's the tangents? Oops. So I'm going to hide a couple things, just the external tangents. Okay. So as I move S left and right, this like always, I wonder if this is like the same line. It looks like the line UV stays the same, right? Is that obvious? So I'm going to draw the excenter. 1 sec, I'm going to look at the chat in just a second. But so we want to draw whoops. Let me just draw this. Actually, you know what? I'll just do it this way. It doesn't, okay, now it just doesn't look true that it passes through the excenter. Maybe I'm missing something. Let me check the chat. Where did we use point D? I don't think we did use point D. I think we just need that AE is tangent. Yeah, point D is pretty much irrelevant. Fj equal Fi. Let's check. Yeah, Fj does look equal to Fi. Let's see. All right, so that probably is important. Homothenity about T proves it. Oh, because triangle MBC is isosceles, so FJI is also isosceles. Yeah. Okay. But I wonder. So yeah, I'm looking at this little mini diagram right here. We're saying N is the excenter. Is that true? Have we ever actually checked that that's actually true? Sorry, it's getting messy. I'm going to erase some stuff in just a second. We'll just check it this way. No, I don't know if, I don't think, oh, because I'm looking at E, not N. My bad. I drop the perpendicular. Yeah, that's the excenter. So then in this diagram right here, one sec. So all we want to show, so if we draw QR, and we draw the excenter, okay, what is W? Oh, the angle bisector. Okay. So so we draw the tangents. Maybe they're already there. I just need to unhide them. We draw these 2 points. We want to show the excenter lies on UV. Whoops. Oh, okay, KU is tangent, PV is tangent. And let's draw the excenter. So that's it. See, that's so weird. The excenter of this doesn't lie on it in this picture. Sorry. Do you guys have an idea of what I'm doing wrong? So this would be the excenter, Z. And let's just check. So yeah, Z is the excenter, but it doesn't lie on UV. So I'm trying to figure out what I'm doing wrong here. You guys see what I'm saying? So Z is the excenter. Well, it can't be, because when I move this around, it keeps changing. So Z can't be the excenter. Oh, I didn't draw Z right. Okay. Sorry. So if I draw the angle bisector of this, okay. So hold on just a sec, guys. Okay, so this, yeah, where did I go wrong? So that's the excenter. Oh, let me look at the chat. Well, UK and O should have been collinear. Maybe the tangent at V should have intersected the circle twice. Oh, yeah, you're right. Okay. So yeah, I need the tangent at V to intersect it twice, and then that would, okay. So let me redo this. So okay. So I have let me draw like a, so this will be the point of tangency, and I have this point, and basically I want to draw a, well, first I want to draw this circle. Oh, because I need BC to be tangent, so I don't really have that much flexibility. It's not as flexible of a situation as I thought. Yeah, no, it's not what I thought. It's not that flexible. My bad. But thanks for catching that. Yeah, you can't just move O2 left and right because then BC would no longer be tangent. I missed that. Okay. Hmm. Is N cyclic with some other points? Yeah, I wonder if it, I thought about that. So N would be the excenter. I'm not sure what points to check. Maybe NF and something. Is that really cyclic, or is that a coincidence? NMO. Yeah, no, that was a coincidence. I wonder if NMG, NGF, no. Let's try something else. And T maybe. Are A, T, N, and E cyclic? Yes. Good call. I missed that. Is that? Let's see why that's true. That's really interesting. So what made you think of that? Did you just sort of guess it? So we need to show, oh really? You just looked at it and it looks cyclic. So angle AEF, AE's tangent, so that gives us some information. We can find angle AEF in terms of the angle, a couple different angles because it's tangent. We want to show it's 180 minus angle ATN. That's probably the easiest way to do it. Or we could show angle TAE is angle TNF. Okay, so if we knew that ATNE is cyclic, really? How does that show? Because I guess we want to show angle TAN is angle TAM. Maybe that's how it does it. So we have TAN is TEN is TEF is TFB. TFB is TBM. Oh, because TFB is HTF, which is MTG, which is TBM, which is TAM. So yeah, if we could show that circle exists, then that solves the problem. All right. Interesting. Okay, so how should we show that circle exists? So we have to use the definition of n somewhere. Maybe we could show, I like trying to show TNF is equal to TAE. Or let's see, maybe TEA. Okay, hold on. Can I extend TN to meet the two circles? Sorry. Also extend TD. Okay. It's equivalent to KP is parallel to EF. But KP is parallel to DO. I don't know if that helps. So DO we want to show is parallel to EF, but E is the tangent from D. Oh no, because OT and E aren't collinear. My bad. K O. Let's see. Is O not necessarily. I'm wondering if we could do just an angle chase to show that this is cyclic. So all we have to show is angle AEN is 180 minus ATN. Yeah, the trick is how do you find ATN, I guess. Or Or we could show AEN is AT 180 minus ATN. Yeah. Maybe there's a better way. A second, guys. I'll be right back. All right. Let's spend 5 more minutes on this. And if we don't see something, then I think I'll move on to the next problem. And then maybe we can come back to it if we end up solving that. I like that observation, though, that ATEN is cyclic. Are GN and I? No. Yeah, it's just figuring out how to define point N, which is tricky. But MC is KP. So you think you've solved it. So MC is parallel to FJ. KP is parallel to DO. MC. So you think you've solved it? Oh, okay. So MC is parallel to FJ, not EF. Yeah, we don't know MC is parallel to DO. So let's see, we want to show ATEN is cyclic. Angle AEN is an angle between a tangent, so maybe that's easier to calculate. But we'd have to show that's 180 minus ATN, which looks a little bit tricky. But ATN, maybe we could break it up into ATG plus GTN. I kind of like that. So ATG is ABT, and GTN is GTN is TFK. TFK help? TFK, TFK is BFK minus BFT. But yeah, TFK is TMC. Wait, no. TFK is, yeah, we'd have to use 0.0. TFK is TIK. Yeah, I just don't know how to use this point K. It's where like, so let's see, TFK. Yeah, we wanted GTK. So yeah, let's see, what is AEN? AEN. So wait, if is angle AEN the same as angle BFE? That can't be. Actually, I think it is. I didn't even realize this, but angle AEF is the same as angle BFE. Because if you extend the two, then it makes an isosceles triangle. I feel like we should have learned that probably a long time ago. So let me see. So angle ATN is ATG plus GTK, which is arc AT plus TFK, which is arc AT plus TFK is TMO. And TMO is, well, angle TMO is just arc TO. So arc AT plus arc TO is arc AO. So angle ATN is equal to arc AO. But yeah, we would have to show that's the same as, so we need to show like arc AO is the same as arc AN, right? I'm not sure. I guess how does that solve it? Because so you want to show AENT is cyclic. That's what you were trying to do, right? And I guess how does that solve it? Because you wanted to show that AENT is cyclic, right? So you found angle ATN, it's arc AO, but is that 180 minus angle AEN? Could be. I just don't see immediately how that's true. Do you think that solves it? Yeah. But there is something we missed all along, and that's angle AEN and angle BFE are equal. We never mentioned that, but it feels like that has to be useful. Because, so we want to show angle ATN is 180 minus angle BFE. So we want to show angle ATB plus NTI is BFE. So BFE is half of arc EF, and this is half of arc EI. And yeah, what if I did this? So basically, is EF equal to EQ? No. Is EP equal to EQ? EP is equal to EQ. The CA, oh no, that has to be a coincidence, yeah. We want to show BFE is ATB, yes, exactly. Or yeah, ATB plus KTI, that's right. So ATB, I wonder, I think this is unlikely, but I'm just going to check it out. Wait a sec. So, okay, I think it's close, but it's not equal. So this is 36.5. This is 36.6. GeoGebra is usually not wrong with those kind of things. So, yeah, it's not true. But all right. You want to move on to the next problem for now and then come back to this later? Yeah. All right. Let's do it. So here's the last problem. So we have it's an X circle problem. I feel like we've had a lot of things like that today. So yeah, I always like using the in-center X-center lemma whenever I draw X circles. I feel like it's usually useful. So, whoops, sorry. But yeah, actually, I think we're gonna want to draw the whole X circle. So whoops. Okay, so let me shrink it a little bit. So this is the X center right here. Whoops. And I'm gonna have to relabel some stuff, but just doing this for now. So that's the X circle. The X circle has center O. It touches BC at M. D and E. So I'm gonna have to rename. Yeah, let me rename this like P, for example. Actually, I'm still gonna keep this circle. So, okay, so D and E are really any 2 points, so that DE is parallel to BC. So let me call this I, and it's already D. It's pretty nice. This will be point E, and then we draw the inner circle of ADE. So let me zoom out a little bit. it touches VE at point N. So by homothency, basically A, N, and F. But I think they define F later, so I'm not going to do it right now. But A and N are collinear at this point. Let BO1. Okay, so we want the center to be O1. O1. That's O1. Yeah, I'm going to want to redraw this a little bit so that O1 is a little bit bigger. But BO1 intersects VO at a point F, and CO1 intersects EO at G. We want to show the midpoint of FG lies on MN. All right, let's hide a bunch of stuff. Actually, you know what? Let me just keep this just for a second, so I could draw these points, and then I'm going to hide it. Okay. So let's draw in all this stuff again. So these are all collinear. Whoops. DE is parallel. I'm going to draw this point now. So obviously A and K are collinear. And F and G. I feel this kind of feels a little like Pappas. So I think FG looks parallel. We want to show the midpoint of FG lies on MN. Maybe I should just hide that circle for now. I'm going to keep the end circle, but okay, so I mean, as we move, okay. So I think FG is parallel to DE. It looks like it in the figure. How do we prove that? Is that obvious? I don't know if it's like Pappas. It feels like some kind of projective geometry theorem, right? That FG is parallel to DE. Let's see. Maybe it's Desargue's theorem. So basically, EFB and EGC are perspective. So by Desargue's theorem, O1, O, and A would be collinear, but we already know that. Okay, so Desargue's doesn't really help us there. Oh, actually, by the converse of Desargue's, that means FG is parallel. So yeah, So FG, I can prove it's parallel to both DE and BC by the converse of Desargue's. Yeah. All right. And then once we know that, so let me draw the midpoint of BC, and then the midpoint of MN. So it's kind of like, are NI and M collinear? No, that just looks like a coincidence. But it might also be worth drawing, like letting AK meet the X circle. So the diagram's getting a little crowded, but if I let AK meet the X circle, then the midpoint of MN, and Q, L, and O are collinear, right? So yeah, so Q, the midpoint of MN, but yeah, we want the midpoint of EF, not MN. Okay. Yeah. I don't know why I was thinking the midpoint of MN. Let me delete some of this stuff. But yeah, OL is parallel to AK. I don't know if that helps, but I used that fact in a recent video. So let's draw the midpoint of EB. So basically A, Q, and L are collinear, and yeah. So the midpoint of FG lies on AL, obviously. It doesn't pass through I, that's just a coincidence, but you have an idea? So yeah, we want to show N, R, and M are collinear. And maybe that's obvious by, yeah, isn't that true just by ratios? Wait, are D, R, and C collinear? No. But does Pappas on DNE and BMC finish? Possibly. So are you sure? Because like F, like, so you said DNE. I mean, where does DN intersect BM, right? It would be like these 3 points, right? So okay, so we'd want to show that this, and this. No, I don't know if those are the right points to use it on. Let me know if you think that is the right strategy. But I don't know if that's the right idea. But we have dn over ne is cm over mb. So basically, yeah, dn over ne is cm over mb. So basically, these are like all concurrent. Hold on a second. But yeah, so but that's not the midpoint of FG because so wait, MN, I think MN also passes through. Yeah, so MN also passes through this point. But I'm not sure how that shows that MN bisects it. I feel like we're pretty close though. Wait a second. Wasn't R the midpoint of FG? Now I'm confused. Oh no, that's S. Oh, Q's the midpoint of DE. Yeah, so we want to show that Q. So we want to show that QS and that X center are collinear. This is weird. FSG infinity. So do you want to project that through, what's the right point to project through N? Okay. So then we would get M, and then, so M would work out nicely. But yeah, I mean, if we're projecting it onto BC, I mean, that's basically just, would be kind of just as hard, I would think, as showing that S is the midpoint of FG. Maybe we could use the gliding principle somehow. So if I label this point right here, DES and BSC are similar. And M and N correspond to each other. So if I take, like, if I take the if I try to use the gliding principle, because yeah, they're oriented the same way. So if I take the midpoint of BC, the midpoint of BE, oops. It won't let me do the midpoint of BE. It's driving me crazy. All I want is to do the midpoint of BE. Okay. E, B. Here we go. So, and then the midpoint of, oh, no. The midpoint of MN. Wait, we wanted the midpoint of I can't even remember what we wanted here. The midpoint of FG, right? Yeah, let me zoom out. Undo a bunch of stuff. So I feel like we're close. We want to show the midpoint of FG lies on MN. Maybe we could use like Desargues again. So we want to show that the line through Q and the excenter passes through this intersection point. Yeah, is there projective geometry? So yeah, maybe it would help. Yeah, we want to show that this point S is the midpoint of FG. Oops, sorry. I doubt that actually passes through L, but maybe it does. Yeah, it doesn't pass through L. I feel like we got this. We have 12 minutes left. Let's see. So KL is equal to LM. We want to show FS is equal to so yeah, we want to show QS and the excenter are collinear. So I'm trying to use homotopy to show that. So NQ, yeah, let's see if I could use homotopy. So, oops. So ANP is homothetic to AKM. It's kind of like we want to show S is the center. This is hard. Let me draw AS. So we want to show QS passes through the excenter, right? Yeah, we want to show that QS passes through the excenter. Can we use homotopy somehow? So Q. So AK is parallel to the line through L and the excenter. Let me try to use that. So AK is parallel to LO. You know what? Maybe there's some easier way, just like using Cheva's theorem, I'm wondering. So if we can show, I mean, so yeah, I'm running out of ideas. I don't know. Let's try it for just a little bit more. Oh, is LS and O1 collinear? Interesting. LS and O1 are collinear. I think at least. Is that obvious? That's because FG is parallel to BC. Yes, so yeah, since S and L are both midpoints, that would have to be true. And I feel like that should do it somehow. So if O, S, and L are collinear, then I think ONS is similar to FM in the excenter. And so I think that means that MN passes through S. Well, no. ON. I feel like this is really close. So, sorry. We want to show OS. Yeah, can we show they're like similar somehow? So we want to show SQN is similar to SLM. And
how could you prove FG is parallel to BC?
oh, so I used Desargue's theorem. So if you look at triangles DFB and EGC, so EC and BD meet at A, DF and FG, DF and EG meet at the excenter, and what's the last? And DF and CG meet at O1. So those 3 points are A, O1, and the excenter. And those all lie on the angle bisector, so they're collinear. So that means that by Desargues, FG has to be parallel to both those.
Oh, okay. So now we have to prove that O1N divided to OM is equal to O1S divided to O.
Or divided by what?
Does O1S is go pass through O?
O1S does not pass through the excenter. No.
Oh, okay.
But O1I does.
Okay.
Let's see. You just have to find a. So yeah, we want to show NQS is similar to. Yeah, I didn't even draw this point right here. And we know that this confers. Okay, this is a little bit tricky. So one more minute, and then we're gonna finish for today. But yeah, I feel like we were very close on this one. So wait a sec. SUM. And so we want to show QN over UM. So that's the similarity ratio. That's the similarity ratio of those two triangles, right? And we want to show that that's equal to SQ over SU. This now it seems like it really should be. Hold on just a sec. So U. Oh, but I think L is the midpoint, not U. Okay, so it's a little bit harder than that. Yeah. Let me just try this one more time. Yeah. All right. So I don't think we're going to solve this for now, but it was a good problem. All right. So that will be it for today. Thanks everyone for joining, and yeah, I'm happy to see that we had a good amount of new members. So as always, if you're watching us on YouTube, like and subscribe. And if you want to join, email me at mgreen801@gmail.com. So it meets every Sundays at 10 a.m. US Central Time. So thanks again, and have a good day.